work on extending state-of-the-art ASR models to Swiss German dialects. So ASR, or automatic speech recognition, is improving fast, and it's becoming ever more present in our daily lives. However, for many low-resource languages, like Swiss German, the advances are limited. So today we're going to show the two main contributions of our work on this topic. First, we benchmarked and fine-tuned OpenAI's Whisper model on Swiss German datasets. And secondly, we explored a novel semantic loss based on the distance between sentence and data. So here is a quick layout of the presentation, and let's go right into it. So first, what's the language situation in Switzerland? So there are 4 official languages. Today we're going to focus on the German part, or rather the Swiss German dialects. There are more than 20, and they all have particularities, their own accents, some special vocabulary. On the right you can see examples of the same sentences in 8 of the major Swiss German dialects from the Swiss dataset. And also importantly, they don't have standardized written forms, so most of the written communication happens in standard German. So this lack of written form results in the fact that there is also lack of annotated Swiss German speech, and this impacts model training for ASR. Thankfully, this situation is improving fast thanks to the efforts of the research community. We can also note that there are more than 5 million speakers of Swiss German in Switzerland. So how can we build a performant ASR model for Swiss German? Based on the fact that the written communication happens in standard German, we decided to focus on Swiss German speech to standard German text. Moreover, the advances in ASR models and multilingual ASR models in particular, and the fact that there are many similarities between the Swiss German dialects is encouraging for the development of a multi-dialect model. And I will not let Clément present the approach of our work and some of its results.
Hello everyone. Okay, so first we wanted to build this Swiss German model, but we wanted to make sure we had data for this. And actually we had data, so we decided to use SwissDial, which is a data set which contains speech from Aargau, Bern, Basel, Graubünden, Luzern, St. Gallen, Valais, and Zurich. It contains transcript from both dialectal transcription and standard German. And for us, the interest in standard German, since there is no precise written forms for dialects. We then use SDS 200, which contains data from 4,000 native Swiss German speakers. So that's roughly 200 hours of audio, which are quality samples. And what's the most important to us is that the dialect distribution is very similar to the actual distribution of speaker in Switzerland. It is also very interesting to us in terms of quality because there is speaker separation, high quality audio, and high quality annotations. Then we use a Swiss Parliament corpus. So this is basically data from Parliament, the National Council, and the Council of States of Switzerland. But the issue with this data set is that there is a lot of dialect from Bern content, and the samples are sometimes noisy. So there is this class imbalance, which was not very convenient for us to make a generalized model for all Swiss German dialects. But we still use it mostly for data augmentation for our training. And finally, we also use FLIR, which is a quite common ASR dataset because it has been one of the training datasets from Whisper, and it contains clean standard German, or more than that, but that was the part that interested us. And we used it mainly to test catastrophic forgetting for our model. Okay, so now that we know that we have data to train our model on, we also selected a few models that would be relevant. So we decided to go with OpenAI's Whisper. That was introduced by Radford and Al in 2022. So there are 6 versions of the model with number of parameters ranging from roughly 40 million parameters to 1.5 billion, so that is an OpenAI scale. It is mostly state-of-the-art for popular languages. So for German, it is state-of-the-art for this. But still, we wanted to compare it with another pretty good model, which was Meta AI's XLSR 1 billion. So released in 2021, based on Wave 2vec, and which contain roughly 1 billion parameters. Both of them have been trained on, as you see, a lot of training data. So 600K hours of multilingual speech data. Even though it's on a lot of languages, that's a lot more than what we have for Swiss German. Okay, so now we have the models. We then decided to see how well they perform without any training. So in a zero-shot manner. So we basically just tested our models on our data set. So basically, we tried without any training, anything. And you see it performs pretty well for Whisper, surprisingly, but it's pretty known to generalize quite well. And for XLSR 1B, it was a bit more complicated. So on the graph, you can see the evaluation on SwissDial for each of the main dialects and on dialectal transcript, sorry. And you see it's pretty bad. So we decided to improve that and to first try a traditional fine-tuning approach. And due to our limitations, we decided to fine-tune XLSR 1B and Whisper Medium. And yeah, we had also good results there, much better than the previous ones, but still we decided to go a bit better, and I'm going to let Victor explain.
So with this fine-tuning on Whisper, we obtained pretty good results, some of them state-of-the-art. However, the evaluation with the where, sir, and blur metrics were limited, in our opinion, mainly because of the differences between the audio and text in vocabulary and tenses between Swiss German and Standard German limit the relevance of the metrics. The fact that the mapping is not one-to-one means that the where and sir metrics often don't represent well how the sentence is understood. The blur metric is usually better fitted for translation tasks, but in this case we only have one branch of transcript, so it also limits its relevance. Those limitations also impact training, because in this case what it means is that even if the model is able to understand well Swiss German, it needs to learn and perform additional translation for certain sentences. So based on this observation, we decided to invite semantics and to leverage advances in large language models in our research.
So yeah, as Victor said, we decided to go with custom metric. Facebook introduced in 2019 something called a semantic distance, which is a pretty general distance. So let's say you have vectors x and y from a general vector space. It's basically 1 minus the cosine distance between them. So basically, you can imagine, in our case, what was interesting is that if you have, for the vectors, embeddings out of a large language model, you can interpret the semantic distance as the distance in the encoder's latent space, basically. So we thought it could be interesting to check that regarding the limitations of where and sir. So in this case, it is also pretty hard to interpret because we can only merely detect how close or far are the vectors, but it's pretty hard to compare distance. For instance, a distance between 24 and 30, we don't really know how to interpret that, and it relies a lot on how well structured is the encoder's latent space. But still, we decided to go with that, and we make it a generalization to a batch, basically taking an average of all pairs, so basically the output and the ground truth in the batch. And from this metric, we decided to derive a custom loss. We still wanted to keep the regular cross-entropy loss that Whisper uses, because we still wanted to get a proper classification error on the tokens that that are outputted by the model, which is what Whisper does initially, but we still wanted to include the semantics. So basically, we went with this idea of having some kind of weighted sum. So as you see in the first example, we weigh the semantic distance by alpha and the cross-entropy loss by beta, and we make sure that it adds up to 1. We chose, to be honest, this pretty arbitrarily due to the lack of time, but we chose for good results that is good enough alpha equals to 0.2 and beta to 0.8. And this modified a bit the training, because in black, as you see, it's the regular training for Whisper, and in blue, it's our contribution. So basically how it works very shortly is that we pass the audio through the model, we get the prediction logits, and we keep the ground truth text on the side. Then we get the prediction string as spread out of the model tokenizer, and then we get back the ground truth, and we pass both of them through ALM. In our case, it's XLM Roberta, because it's multilingual and knows pretty well German. And out of XLM Roberta, we have these fresh embeddings that we just use to compute our semantic distance. And from that, we have our custom loss, and then we just backpropagate in a regular fashion. And we found out that the best setup for this, pretty arbitrarily, we didn't really have the time to make extensive tests on the hyperparameters, etc. But was for the data shuffle concatenation of SwissDial and 20% of SPC. Why 20%? Is that we wanted to have the same number of samples from both data sets. We had pretty good results already, and then we had access to SDS 200, so that sounds a bit arbitrary to just, after that, fine-tune it for 2 epochs. That was the main reason. So we just used our best model and then just retrained it on SDS 200 for 2 epochs. And it's not very important. But with this setup I just described, we had pretty good results. But we wanted first to evaluate how good of a metric could semantic distance be. So we evaluated it on the test set of our dataset to check first if it was coherent, and then if that improved using our customers. So we see the first row is vanilla Whisper. So we can see that there is a good semantic distance for all of them, for all of the data sets, and of course it's better for others because standard German, Whisper has been trained on it, even though if it's the set that very, very good results. So we can recognize there the good generalization capabilities of the model. But what's interesting is that when we look at the fine-tuned Whisper, so the next 2 rows, the one with the regular cross-entropy loss, so our row fine-tuning, we get better results, of course, because we trained the model on this data set. But the interesting part is that when we use the semantics loss, the custom loss, we still notice improvement in there. So that's a pretty good sign that it works pretty good. And then the main results with the traditional metrics there. We see that we had the best order rate for SDS 200, or at least at the time of the project, using our semantic loss. But we also noticed quickly that there is some catastrophic forgetting, at least on the first data set, because a regular Whisper is around 3 or 5 of where 7 German. So that's something we have to take into account. But still, we're very happy with the results. XLS O1B was a bit less good than Whisper, but we think it's pretty logic due to the generalization capabilities that are really proven for Whisper. And then Victor talk about interesting examples we run into.
So we're a bit short on time, so I'll go quickly. First, I want to precise that an interesting thing. Sorry.
You have 5 minutes left.
Oh, okay. Thank you.
No need to rush.
So we realized that using the semantic loss resulted in improvement in semantic error without major loss on the classical error. So that was encouraging. So here, also one critique of the semantic distance is that it's difficult to interpret because it results from a deep learning model, which are often black box, and it would also depend on the LLM we use. However, we argue that classical losses are also sometimes difficult to here you can see examples. For example, in the first sentence, you see that sei ein strategischer Entscheid is compared to the ground truth, which is sei ein strategische Entscheide. And here we get a word of 50. So the sentences are pretty close, but we get pretty bad metrics. Whereas the semantic distance is able to recognize that the two sentences are very close to each other. In the second one, we see a very typical example for Swiss German, where the tenses are not the same as in standard German. And so we get very bad word of 60. Ser is also bad, and below is 0, which is terrible. However, semantic distance once again recognizes the similarity between the two sentences. Third example would be the inverse, where the two sentences are very close, but in Dorfstrasse, the model understands Dorfstrasse, which is a very important word in this sentence, and that can have a big impact on its understanding. And we see that some distance is much higher than in other sentences. The fourth one, everything is pretty good because we only see a small difference in Asylbewerber and Asylwerber, which I believe are synonyms. And the last one would be a case where semantic distance is quite high despite two sentences being very similar. So that's an example showing that we still need to do additional research in this method for evaluation. Maybe it comes from the fact that 22 and 10 could be confusing. So maybe the model believes that the sentences have very different meanings. However, from this few cherry-picked example, we still believe that this is a path to explore that would be interesting for these kind of tasks.
And one good thing is that for the previous results I showed, I think these errors on the past tenses affect a lot the word error rate we have, meaning that usually we run into the results, and for most of the results, the transcription was almost perfect when it didn't involve past tenses, but then when it involved past tenses, most of the errors we had was this inversion from pertinent to composed past, I think it's called. That implied that further work could be done like this and probably involve conjugation. For the future steps, of course, we could see additional fine-tuning on Whisper with more data, more high-parameter tuning, having something more exhaustive. We could also do hyperparameter tuning on the loss, because for now we choose these arbitrary constants, but we could also leverage how it impacts the final results. And also we had the idea to maybe train ASR models for a few epochs to learn about the accents from different contents and then get a better understanding and maybe get new word embeddings, new tokens, and then train token decoder only for translation. So that's another idea for future work, if some of you are interested to continue this. And then also maybe model pruning. And we also figured that it could be limitations because we noticed first that Whisper Large was the best model in our zero-shot evaluations, but we didn't, of course, have the resources to fine-tune it. We were very low on resource and time. And also, catastrophic forgetting happened there compared to our original datasets Whisper has been trained on. That is also something that could be fixed, that maybe isn't too relevant either if it's special system. And of course, further investigation to make semantic loss more useful. That was the conclusion. Thank you for your attention.
Thank you. Questions, please.
It seems to me that your model is cross-entropy loss superior than to semantic distance, but you didn't have time to fine-tune semantic type around this. Do you think you can fix that?
Of course. Maybe maybe one precision on this is that we didn't want to have only the semantic distance as a loss. So what we call, maybe you can show the slide.
But you didn't fine-tune the parameter alpha, right?
Exactly, no, we didn't. We just...
The question is, do you expect by fine-tuning alpha that you get semantic distance loss superior than cross-end?
So I'd say that one of the advantages maybe of the semantic distance is that it relieves pressure on the sentences with, for example, different tenses. And I think this could benefit training because it doesn't force this translation task on the model. Of course, it wouldn't improve the classical metrics like where, but if we focus on the sentence meaning, that would help the model. And I believe in our results, actually some of the models trained with semantic distance, they also perform better on the classical metrics. It doesn't on SPC, but I think we use much less SPC data in the training than SDS, for example. But of course, those are points we need to explore further.
Yeah, but it's, on Swiss style, it's a huge difference in the voice model.
Yes, that's true.
And in SPS 200 only is relatively small difference.
Yeah,
So
that's
in the best case, or in the worst case, your semantic loss will be the same as cross-end, right?
yes.
But maybe you can get a better result with some fine-tuned alpha.
Yes, hopefully. I mean, that's something we would like to see, and that would need to be fine-tuned. But of course, the objective of the model then is not the same. So maybe we will observe worse results with respect to these metrics, but improvement in the quality of the predictions.
And semantic loss is also not perfect because if you show us the table with the semantic distances, example 4, I guess.
Sorry, which one?
The list of examples,
the list
the
of-
actual text
Oh, yeah.
examples.
No.
No?
The second last one. Our Syrian, no, that's the second last one. Our Syrian started
No.
in 9
sorry, second last one, yeah, sorry.
Yeah, you have semantic, very small semantic distance, but prediction is really, it's not correct.
No, it's not correct, indeed. But that's the...
I'll see you there. Okay, never heard
Yeah, that's the issue. Also, maybe I can add on the main results. Of course, we don't see many improvements. It's based on the traditional metrics, which, as we explained, are maybe not the most adapted ones to this specific task. Because, as we said, the where, SR, and blur are not really suited for this task. We'll see when to present it to compare with traditional metrics, but that's maybe not the main direction of improvement of this new one. Yeah.
So you introduced a model for the loss. Do you have an idea what is the impact of runtime for one training? Because you do this.
Of course. Actually, it was, I think, I don't have precise numbers in mind, but of course it took a bit longer when we used this model. But the cool thing is that it was frozen. We didn't try to retrain the XLM Roberta model. So that actually there was just a forward pass at every computation of the loss for each batch. So yeah, that slowed the thing a bit down, but it was not too bad. But I think it was mostly due to the good GPUs we had, because otherwise we couldn't have done this. More questions?
Maybe we can still stay with these results. I was curious about how did you do the fine-tuning? So did you do per data set? So for each data set you take some for fine-tuning and then some for testing?
Yeah.
You pulled together everything? So did you do any cross fine-tuning testing?
It was a bit messy. So this is just the results of the test set. Maybe that was not clear, but each column is the test set of the data set and the different metrics we use. But for the fine-tuning themselves, As we said, it was a bit messy. We had imbalanced data sets in terms of number of samples. So we didn't want to influence too much the results with one data set compared to the other, but we still need to include both because we like data. So we said, okay, let's take SwissDial, which was high quality, and then take the corresponding number of samples from SPC, so we had around the same number of samples, and then we had SPS 200 a bit later. And it still was the highest quality data set we had. We still wanted to train it and to see how well we could perform. Is that practical? I don't know, but we wanted to make the best model we could based on that. But it sounds a bit sketchy.
It was because of your time constraints, right? Because
Exactly.
this was like a semester project, so
Exactly.
you were improvising a bit, let's say.
Yeah, we had the data set 3 days before we had to finish the project.
Okay, wow.
I mean,
Yeah, that's
it's
what we
okay.
could.
Don't test on the training part.
Exactly, so this was well done.
Actually, one of the main reasons we focused on SDS is, of course, its quality, but also they define very clear training and testing sets, and it's multi-dialect, so that was our main focus.
Thank you very much. Another, yeah, one more question? And then
So maybe I missed something at the beginning, but here you're trying to achieve both some kind of transcription or speech understanding and then translation. Wouldn't it be better, in your view, to try to separate the two tasks? So transcribe Swiss German and translate it to High German.
Sure.
What's
The issue with that, for us, I think that's the better approach indeed. But the issue with that is that we would have needed to retrain a whole tokenizer to have new tokens for Swiss German, and we still wanted to use the pre-trained power of Whisper in this, which was trained on German, and we still get good results at least. And still, since there were also no agreed written form for all dialects, we thought it made more sense to go directly to standard German. Or otherwise it would have been case by case and there would have been even less data for each dialect.
So if I can just add something to that. In the discussion we indeed had this idea that maybe we can allocate the weights, the error weights on the translation task with semantic distance, and then maybe after only a few training on the raw data and classical training, we focus this part of the training would maybe help the model understand what Swiss German sounds like. And then do a second training of only the token decoder. And focus this part of the model on